Look at the skyline of Dubai. It is a masterpiece of modern marketing. Every year, millions of tourists arrive with a single destination in mind. They stand at the base of the tallest structure ever built by human hands. They look up at 828 meters of shimmering glass and steel. They see a miracle of engineering. They see the ultimate symbol of endless wealth, unshakable stability, and a tourism industry that supposedly knows no limits. But this image is an illusion. The marketing brochures tell a story of triumph over the desert. The physical reality tells a very different story. If you step back and view this glittering monument through a thermal imaging lens, the illusion instantly shatters. You do not see a cool, passive monolith. You see a structure burning in bright reds and harsh yellows. You see a machine operating under terrifying thermal stress. The truth is that the Burj Khalifa is not just a building. It is an incredibly fragile life support system. And right now, deep within its mechanical core, a slow and invisible crisis is unfolding. A crisis of mechanical fatigue, extreme physical pressure, and unsustainable economic costs. The glittering glass facade is hiding a terrifying vulnerability. And when this cooling system finally reaches its breaking point, it will not just threaten a single building. It will expose the fatal flaw hidden beneath the entire Dubai tourism miracle. To understand the scale of this looming disaster, you must first understand the hostile environment surrounding this tower. Dubai is not just hot. It is a tropical furnace defined by brutal environmental drought and relentless solar radiation. The exterior of the Burj Khalifa is wrapped in more than 120,000 square meters of glass. In the architectural world, glass is beautiful. In the world of thermodynamics, glass in a desert is a catastrophic liability. It acts as a massive magnifying lens. During the peak summer months, the ambient temperature outside easily surpasses 45 degrees Celsius, which is over 113 degrees Fahrenheit. But inside, the luxury hotels, the exclusive restaurants, and the corporate suites demand a constant, perfectly controlled climate of 22 degrees Celsius. This creates a terrifying temperature differential. The tower is essentially a vertical greenhouse trying to survive inside an oven. To prevent the interior from boiling, the building cannot rely on passive insulation. It must actively fight the environment every single second of every single day. If the active cooling system were to shut down completely, experts estimate that the interior temperature would become unlivable within just 2 hours. The air would stagnate. The glass would trap the solar radiation. The luxury restaurants and high-end retail spaces would transform into lethal glass traps. The entire hospitality ecosystem inside the tower relies absolutely on this mechanical heartbeat. The city has marketed this building as a permanent fixture of the global tourism landscape. But permanence is a lie when your survival depends on a machine that can never, ever be turned off. This brings us to the beating heart of the illusion, the machine itself. The cooling required for a structure of this magnitude is so massive that it cannot be generated inside the building. It requires a dedicated external infrastructure known as district cooling. Deep underground, away from the eyes of the tourists, massive industrial chillers are working desperately to freeze millions of gallons of water. This chilled water is the lifeblood of the tower. But creating the cold water is only the first part of the problem. The real nightmare begins when you have to move it. Imagine the sheer physical weight of water. Now imagine trying to push a solid column of that water straight up into the sky. This is the brutal reality of hydrostatic pressure. The central pumps must force thousands of tons of chilled water up an elevation of over 800 meters. Gravity is constantly fighting back. This creates a crushing internal pressure within the plumbing infrastructure. The pipes located at the lower levels of the tower are subjected to forces that are difficult to comprehend. The water is pushing against the steel and copper walls of the pipes with the force of a high-speed train. Every weld, every joint, every valve must hold back this relentless pressure. The engineering required to contain this force is brilliant, but it is not immortal. Metal has limits, and under constant, extreme pressure, even the strongest industrial steel begins to experience microscopic deformation, a hairline fracture, a flaw no thicker than a single strand of human hair. If a weakness develops in a primary riser pipe under this kind of hydrostatic pressure, it does not simply leak, it ruptures with explosive force. The water hammer effect could tear through mechanical floors, destroying electrical grids and flooding critical infrastructure. The building is engaged in a constant, silent war against its own internal fluids. And then there is the paradox of condensation. The marketing campaigns love to highlight the building's green initiatives. They proudly state that the cooling system harvests over 15 million gallons of condensed water from the air every year, using it to irrigate the surrounding parks. It sounds like an environmental victory, but think about what that actually means. Condensation occurs when extreme cold meets heavy humidity. That 15 million gallons of water is not a feature, it is a symptom. It is the physical evidence of the building sweating. It is the visual proof that the cold interior is locked in a desperate, losing battle against the humid desert air pressing against the glass. The air conditioning system has to work incredibly hard just to strip this heavy moisture from the air before it can even begin to lower the temperature. Every drop of that recycled water represents a massive expenditure of electrical energy. The system is fighting gravity, it is fighting pressure, and it is fighting the very atmosphere of the Arabian Peninsula. But there is a much smaller, much more vicious enemy attacking the system from the inside out. The desert is not a quiet, empty place. It is an active geological force. When the wind blows across the Arabian Peninsula, it carries millions of tons of microscopic material. This is not the soft, round sand you find on a tropical beach. Desert sand is primarily composed of silica, quartz. It is jagged, highly abrasive, and structurally similar to microscopic razor blades. The Burj Khalifa requires massive intake vents to draw air into its cooling towers and heat exchangers. And despite the most advanced industrial filtration systems in the world, the finest particles of silica dust always find a way inside. They bypass the primary filters, they slip past the secondary screens, and they enter the mechanical bloodstream of the cooling system. Once inside, these silica blades begin their slow, methodical work of destruction. They act like airborne sandpaper. They enter the high-speed turbine fans. They grind against the lubricated bearings of the massive compressor units. They coat the delicate fins of the heat exchangers, creating a layer of abrasive insulation. Every hour of every day, the silica is scraping, scratching, and wearing down the moving parts of the life support system. But the silica is not working alone. It has a partner in this destruction: thermal cycling. The temperature in the desert fluctuates wildly between the searing heat of the day and the rapid cooling of the night. Inside the mechanical rooms, the temperature shifts as the chilling units cycle on and off to meet the demand of the tourists inside. Physics dictates that metal expands when it is hot and contracts when it is cold. The miles of piping, the heavy valves, the massive steel brackets holding the system together, they are all breathing, expanding, contracting, stretching, shrinking, day after day, year after year. This constant movement creates a phenomenon known as mechanical fatigue. The molecular structure of the metal slowly begins to weaken. The joints become stressed. The seals between the pipes begin to harden and crack. You have thermal cycling pulling the system apart from the outside, and silica dust grinding the system down from the inside. It is a perfect storm of mechanical degradation, and this degradation triggers a deadly feedback loop that the engineers cannot stop. As the silica damages the heat exchangers and the thermal fatigue weakens the valves, the overall efficiency of the cooling system begins to drop. The machine can no longer produce the required amount of cold air with the same amount of effort, but the demand from the building never stops. The tourists in the observation decks still need their perfect 22 degrees. The luxury restaurants still require pristine air quality to maintain their elite atmosphere. The hospitality sector inside the tower cannot tolerate a fluctuation in temperature because a drop in comfort means a drop in revenue. So, to compensate for the lost efficiency, the building's central computers force the cooling system to work harder. The pumps push more water. The compressors spin faster. The fans draw in more air. The system is deliberately pushed past its optimal operating parameters. It is forced to overclock, but when a machine works harder, it draws more electrical current, and when it draws more electrical current, it generates more internal heat. This is the death spiral of thermodynamics. The system generates excess heat simply trying to produce enough cold. This excess heat accelerates the thermal wear and tear on the components. The harder the system works to fight the desert, the faster it destroys itself. The electricity required to maintain this overclocked state is staggering. The cooling system alone consumes enough power to sustain a small, independent city. The financial cost of this electricity is a heavy burden, but the mechanical cost is far worse. By forcing aging, abraded machinery to run at maximum capacity, the operators are drastically shortening the lifespan of every single component. The parts are wearing out faster than the original engineering models predicted. The desert is accelerating the clock on the building's mortality, and this brings us to the nightmare scenario that the real estate developers and tourism boards refuse to discuss in public. What happens when a critical component in this overclocked, fatigued system finally shatters? What happens when the machine stops? Let us look at a highly probable failure scenario. Imagine a primary chilled water transfer pump fails on mechanical floor 155. The bearings, ground to dust by years of silica infiltration, finally seize. The motor burns out. The pump stops dead. Instantly, the hydrostatic pressure within the localized loop spikes. The water hammer effect violently shunts thousands of gallons of water into secondary pipes that are already weakened by years of thermal cycling. A secondary valve blows. The cooling loop for the upper 20 floors loses pressure and shuts down. The temperature in the highest luxury suites immediately begins to climb. The automated systems trigger alarms, and the maintenance crews are dispatched. But this is where the genius of the Burj Khalifa becomes its own worst enemy. You cannot easily repair or replace heavy industrial machinery at an altitude of 600 meters. When the building was constructed, massive external cranes lifted these 10-ton pumps and compressors into the sky. The building was literally built around the mechanical systems, but those construction cranes are gone. They were dismantled over a decade ago. If a massive compressor dies today, you cannot simply order a new one and drop it through the roof. The logistical reality is a nightmare. The replacement parts, weighing thousands of pounds, must be broken down into smaller pieces. They must be carefully loaded into the internal service elevators. They must be transported up hundreds of meters, unloaded in tight mechanical corridors, and reassembled by hand in extreme conditions. A replacement operation that would take 3 days in a normal ground-level facility could take 3 weeks in the upper levels of the Burj Khalifa. But the building does not have 3 weeks. The restaurants do not have 3 weeks. The tourists will not wait. Within 24 hours of a localized cooling failure, the affected floors would become entirely unusable. The luxury tenants would be forced to evacuate due to extreme heat and stagnant air. The financial losses for the hospitality sector would be immediate and severe. But the real damage would be to the brand. Dubai's entire economic model is built on the perception of flawless, uninterrupted luxury. If the crown jewel of the city cannot keep its own lights on and its air cold, the illusion is broken. The world would see that the miracle is just a machine, and machines break. This mechanical vulnerability exposes the deeper economic fragility of the entire Dubai tourism model. The city is currently facing a silent crisis of oversupply and unsustainable expectations. There is enormous pressure on the hotel industry, the retail sector, and the real estate market to constantly deliver record-breaking profits. But these profits are built on an infrastructure that is growing older, more fragile, and exponentially more expensive to maintain. The Burj Khalifa is approaching a critical age. Industrial cooling systems in harsh environments typically have a lifespan of 15 to 20 years before they require massive, systemic overhauls. The tower is entering the end of that life cycle. The maintenance costs are no longer linear. They are following a J-curve, shooting upward exponentially. As more parts fail, more efficiency is lost, and more energy is required to keep the system running. This is the hidden time bomb of Dubai real estate. Investors buy into these mega projects believing they are acquiring a permanent asset, but they are actually buying a liability. They are buying a share in an immensely expensive life support machine that requires constant injections of capital just to survive the climate. The developers can build higher, they can build faster, but they cannot engineer their way out of basic maintenance costs. As the cooling system of the Burj Khalifa requires more drastic and expensive interventions, who will pay the bill? The service charges for the residents and commercial tenants will have to skyrocket. If the costs become too high, the businesses inside will lose profitability. If the restaurants and luxury suites cannot afford the maintenance fees, they will close. And if the interior of the tower begins to empty out, the core attraction of the city loses its value. The tourism crisis in Dubai is not just about empty hotel rooms or shifting global travel trends. It is about the fundamental, physical cost of keeping the desert outside. When the cost of artificial survival exceeds the revenue generated by the tourists, the entire economic equation collapses. The mechanical fatigue of the Burj Khalifa is a perfect mirror for the economic fatigue of a city that was built too fast, too large, and in direct defiance of nature. This escalating cost of survival does not stop at the edge of the Burj Khalifa. The exact same mechanical and financial pressures are quietly squeezing the entire hospitality sector across the city. Dubai relies on a massive network of district cooling plants to keep its megamalls, luxury resorts, and high-rise hotels functioning. But district cooling operates as a localized monopoly. The hotels cannot simply switch providers if the utility costs get too high. As the infrastructure ages and the thermal stress from the desert takes its toll on the grid, the operational rates begin to climb. This creates a silent crisis for hotel operators. They are caught in a financial vice. On one side, they face intense competition from an oversupply of new hotel rooms flooding the market, forcing them to keep room rates competitive just to attract tourists. On the other side, their fixed operational costs, driven by these massive cooling bills, are rising exponentially. A luxury hotel in a temperate climate can reduce its air conditioning during the off-season to save money. A hotel in Dubai cannot. The chillers must run continuously just to prevent the interiors from degrading. This means that even during the slower summer months, when occupancy rates naturally dip and revenue slows down, the mechanical burn rate remains terrifyingly high. The gap between what a hotel earns and what it must spend simply to remain habitable is shrinking rapidly. For smaller luxury operators or older properties that lack the absolute highest tier of brand protection, this math is becoming unsustainable. They are forced to cut corners on renovations, reduce staff, or lower their service standards. This immediately damages their reputation in a market built entirely on the promise of absolute perfection. The cooling crisis is no longer just an engineering problem. It is actively eroding the profit margins of the very industry that Dubai relies on to project its wealth to the world. The battle between human engineering and thermodynamics only ever ends one way. Nature has infinite time and infinite resources. The building only has the budget of its investors and the endurance of its steel. The specialized cooling system of the Burj Khalifa is an absolute marvel of human ingenuity. But it is fighting a war it is mathematically destined to lose. Every grain of silica, every degree of temperature shift, every drop of condensed water is a small victory for the desert. The tower will not collapse physically. Gravity will not pull it down. The engineering of the superstructure is far too strong for that. But a building does not need to fall down to die. It only needs to become too expensive to cool. If the mechanical heart fails, and the J-curve of maintenance costs bankrupts the operational budget, the building will simply cease to function. It will stand exactly where it is. But it will be empty. A hollow, superheated pillar of glass and steel. It will transition from being the ultimate symbol of a booming tourism empire to becoming the world's tallest tombstone, a monument to the dangerous illusion that money can permanently rewrite the laws of physics. The warning signs are already there, written in the wear and tear of the metal, hidden behind the flawless glass facade. The question is not if the machine will reach its breaking point. The question is how much more money the city is willing to burn before they admit that the desert is taking its territory back. This video is an independent documentary analysis based on publicly available data, engineering principles, and thermodynamic realities regarding large-scale HVAC systems in extreme climates. The structural and economic scenarios discussed are analytical projections, not statements of immediate fact. This content explores broader macroeconomic vulnerabilities and mechanical constraints. It does not intend to attack the residents, the workforce, or the businesses operating within Dubai. The information presented here does not constitute financial, investment, or personal travel advice. Economic and engineering conditions are subject to change, and viewers should conduct their own research before drawing definitive conclusions. If you value documentaries that look beyond the glittering skyline and examine the hidden mechanics of our modern world, make sure to subscribe. We strip away the marketing brochures to find the real stories hidden in the data. The next major warning sign is rarely where the official narrative tells you to look. Leave a comment below with which mega project you think we should investigate next, and we will see you in the next analysis.